So I know that activity that we did on Friday is a hard one, and you probably go away from it. A lot of people probably felt this way. You go away from it feeling like, geez, I'm still confused, or, I'm still not quite sure. I hope that after doing some of the practice, I hope you tried some of the practice, and after doing some of it, it started to come together. But today we're going to do a whole bunch of examples where I'm going to try to just kind of teach the different strategies, and now that you've had a chance to work on it a little bit yourself, and then we're going to go back over it after today, I hope you do start to develop a bit more confidence about this. If not, keep working on it and keep asking questions. There wasn't homework tied to that activity. It was just like finish the activity. So if you didn't, you can still go back and do that. I think there's a fair bit of homework connected to this lesson. So same thing over the next couple of days. Chip away at it, like keep trying it, and that's all you can do is obviously just keep working away at it. Tomorrow we do sketching, and there's only, I think, 2 sketches in the homework, like it's kind of light. So you have time over the next few days to finish any homework from Friday, any of that activity, finish any of the homework from today, and do the sketches. Tomorrow sketching, the next day is something very different. So it's a one-off. I don't think you'll find it all that hard, but it is very specific, very different. And that wraps up the unit. Then we have review and test. Okay, so just keep that in mind. All right, here we go. So first thing that I think I'm going to do is draw these graphs. This is a function. The entire function is a combination of x, which is linear, right? Just a linear function, and e to the x, that exponential that we've been exploring. So as I said before, some people, a lot of people, I think most of us, would find it useful to actually graph these so you can look at them. But you might be able to just visualize without graphing. A lot of what I'm going to do is like suggested strategies. So these are different ways that you can think about it. In fact, I think for this one and a couple of the others, I'm going to show you sort of multiple ways that you could approach it, which I hope will help build kind of an overall understanding of what's going on here and just help you kind of get the picture of it. But then it's up to you to figure out which one works best for you. And on the test, it will say, there will be a question like this where it's not a full sketch. And there might be like an A, B, C. So there might be a few sort of ones that you have to go through where you have to determine the asymptotes and end behaviors around the asymptotes and show some evidence for why you came up with your conclusion. But it's not as specific about the exact evidence that you have to show. Okay, so you got to come up with something, and then if you have further questions about that, obviously you can ask over the next couple of days. But just keep that in mind that I'm going to kind of show a whole bunch of different ways that you could think about it, and we're going to write it all down, and then it's up to you to kind of pick the one or the two that you like best. So I'm going to start with vertical asymptotes. Thank you. Any reason to think that this function would have a vertical asymptote? Why do functions have vertical asymptotes?
Because of the denominator being 0.
If they have a denominator equal to 0, and we even saw some that had a denominator, again, don't write this down, something like that can never equal 0, so it doesn't have vertical asymptotes. Like we've seen that. But this doesn't have a denominator. What's the other reason why a function might have a vertical asymptote? Victor?
It's logarithmic.
Yeah, if it's got a log in it, and this one doesn't. So there's no reason to think that this has a vertical asymptote. We talked about domain a couple of days ago. The domain of y equals x is that x can be anything. The domain of e to the x is x can be anything. So adding two numbers together will always give you a number. There is no reason to think that there's a place where this function doesn't exist. So this just has no vertical asymptote. So then we start to think about, what about the horizontal asymptote and or oblique? And these ones are different, where they can have two different horizontal asymptotes. They could have horizontal going one way and nothing going the other way. They could have oblique going one way and nothing going the other way. That happens fairly often. I think we're going to see that. So different things can happen, and this is where it's not like the rule in rational functions where you look at the degree of the numerator and denominator. Like, there isn't a rule. There are specific types. So there was one that we did when we did the full sketching on the first day, and there was a couple in that activity that turned out to have oblique asymptotes. And if you did enough of these, you might start to recognize them, and you could kind of say, oh, I think this one might, like right off the bat, I think this is one of those types that has a oblique asymptote. But I also think you have to consider the strategies that we're going to talk about how to explore what's going on. So I'm going to start exploring to the left. What does x do? This is kind of a weird thing to write, even bother writing down. As x because the function is y equals x. So as x goes to negative infinity, what does x do? Almost too easy of a question that makes it hard. What does it do?
Goes to negative infinity.
Goes to negative infinity, but like, that's what it does. It's just, this is like x equals x, right? Like, so, or y equals x. So x goes to negative infinity. What does e to the x do? It goes to 0. So this is the kind of question where you've got a function that is the combination of multiple functions, and part of it is going away. It's not exactly 0, but it's close to 0. So what do you think is happening here? Victor?
Would there just be an oblique asymptote on the left side?
Yeah, there's an oblique asymptote going just that way. We have not talked about to the right. So again, in rational functions, when you have an oblique asymptote, it's oblique both directions. It's the same oblique asymptote going to the left and the right. That is not the case for these. So we have only talked about going to the left. The e to the x part is going away, so we're left with y equals x approximately, which is an oblique asymptote. So at some point in your solution, you have to write the asymptote. And we have to determine its behavior. In other words, is it above or below? And this is where I'm going to explore a couple of different ways of doing this. It's kind of interesting, I think. In this function, if you look back at how, you remember when we did rational functions that had oblique asymptotes, we would do long division or synthetic division and rewrite the function with the oblique asymptote and the remainder part. This is already written that way, isn't it? This is your oblique asymptote, and this is your remainder part that's going to 0. Like, this function is actually written in that form to begin with. So our remainder is e to the x. Anybody want to think about that for a second? What's relevant about e to the x? In terms of how we have to consider it as the remainder.
It's always positive.
It's always positive. Why is that relevant? Why is that important? Victor?
Could it tell you like what, like that it's above, approaching above the oblique asymptote?
Yeah, absolutely. Right? So, and again, we're looking at to the left. We're not talking about to the right, because to the right it gets big, and that is not a remainder. That is doing something to the function. But to the left, it is getting close to 0, but it is positive. This version of e to the x is positive. So e to the x is always greater than 0. So your remainder is greater than 0, so you're going to be above. I could also sub a value in. What's a good value? So if r at x is e to the x, r at, what would you pick? Negative 100. That might be too big. Yeah, kind of ugly. How about negative 10? Like you could also do 0.00005. You could also plug a value into your remainder and check it just like we did. Absolutely, that's a strategy that you could use. What's the other way? And I mean, I don't prefer this way just because I think it's more work, but you could do it this way. I'm going to choose negative 10 again, and I'm going to sub it in to the original function. This is probably not something that we've really, might have talked about it, but never used it as a strategy because it tends to be more complicated. Nine, 5. Nope, not y. And then r at negative 10. Whoop, that's not what I want. I want y equals x. Your oblique asymptote at x equals negative 10. This is a lot more work, I think, but it is kind of a good thing to point out at least once. What's happening here? How can I interpret that? Like it's giving us the same conclusion. We already know that we're above the asymptote. Victor?
For y at x, x should be, well, like x should also be negative, y should be negative 10 if it's on the line and following the line, but if it's negative 9, that means it's a bit higher than where the line should be.
Yeah, you're just comparing the output of your oblique asymptote and the output of the actual function and looking to see is it above or below. So this would be negative 10.0000001 or 5 or whatever. If this would be, if it was below, but it's above, but because the numbers are negative, it's a little bit awkward and all that stuff. So to me, this is way more awkward. But that is what's happening. The actual function, the output value would be negative 9.99995. But the oblique asymptote would be negative 10. Compare those two numbers and see where you're at. But if you can come up with sort of a resolution for what's happening with the remainder part, if you see it that way, that's probably easier. And you just test the remainder part like we did back in advanced functions. And even in this course when we did sketching, test the remainder part and see if it is, or in this case, the remainder part is always positive, so why not just look at it that way? Any questions about that part so far? I think that's the first time we've looked at an oblique asymptote together. So that's one of the types where you have an oblique asymptote. Go back to that original function. x plus e to the x. If you look at the question in the other question in that activity, it also has e to the x plus something or minus something, could be either. It's in the denominator, which changes things a little bit, but it also caused an oblique asymptote. So those are kind of the types where you're going to get that happen if you want to sort of memorize or think about the different things and make those connections. So that is only to the left. Now we have to do to the right. X goes to positive infinity. E to the x goes to yep. Yep. So what does y do? You got a really big number and you're adding another really big number. It's just going to infinity, right? So I would say that one's kind of done. You could test it. Let's do it. Why not? Like I said, I think you want to come up with a theory, a hypothesis, conjecture, compare the different functions, how are they interacting, adding, subtracting, dividing, multiplying, whatever it is. Think about what's happening and then check it on your calculator. Does that number mean anything? Could there be an oblique asymptote going that way and it's approaching it? I mean, I suppose, but that number looks pretty random to me. What if I put 100 in? I bet you that's going to kind of explode the calculator. I mean, it's just getting really big, right? That's the kind of evidence that you could provide. You could write out the different parts, adding. You're adding big numbers. You could write out a point to show that you checked on your calculator. This is the kind of evidence that you could show, that you have to show. You don't necessarily have to show each part for every question, but that's the idea. I think I have the graph here. Whoop. Not what I wanted to do. So that's what it looks like. Oblique asymptote going that way, and then just goes off. Any questions about that one? Okay, next. This one's a little tricky. I'll help get it started, but it's very similar. You're adding a linear part with an exponential part. What's different about it? Well, I said adding. You're adding the negative version of something. What else is different? We're subtracting here, and we have a negative here. How will that impact things overall? So let's look at that together, and then you might be able to do a bit of this one on your own. Okay, so forget about the fact that you're subtracting. Let's just think of this as a function, e to the negative x. What does that do? What does a negative x do?
It flips the whole graph.
Where, how though?
It will flip it down.
The negative out front would flip it down. So this negative flips it. What's the other way that you can flip it? It's either in the x-axis or in the y-axis, yeah, so it's going to flip it this way. So this is y equals e to the negative x. And again, I don't want to overcomplicate things. I think this is the best way to do it. This is how I like to think about it. But this might be a personal thing. So I'm going to probably, for myself, think about e to the negative x and think about that I am subtracting it. But you could consider this function, negative e to the negative x. What is this is like a negative a value. If you think about transformations, you did this in grade 11, transformations of exponential functions, not base e, but other bases. So you've done this before. And this is a negative a value. What does a do? That's the one that flips it this way. So that would look like this. And then you're adding them. I'm going to think about subtracting, and I'm going to think about the blue graph, the top graph. But you could do either. But you kind of have to pick one and stick with it. Don't flip-flop back and forth, right? You got to decide what you're doing. What's the other thing that we have to do before I can move on? What did I start with in the first example? We started with, John? Vertical asymptotes. Does this have a vertical asymptote? Whether or not the answer turns out to be yes or no, it has a negative exponent. That's a denominator, right? Isn't this the same as 3x minus 1 over e to the x? Which is 3x e to the x minus 1 over e to the x, just getting a common denominator. So for vertical asymptote, what about that? Yeah, that's the, huh?
No.
None. No solution to this. So still no vertical asymptote. But you have to consider that again, that's your evidence. You're showing that it does have a denominator, something that you should consider. To be honest, the tricky thing about this as well is I said this the other day, there's lots of different kinds of questions, and on the test, you're only going to get one or two of them. So are you going to get an e to the negative x question? You might not. But it's something that you should consider. It's always something to remember. Horizontal and oblique. Let's do the same thing. This is where I'm going to let you try to take it over and at least see what you can come up with a little bit. Oh, I'll do this part. So what is 3 to the x doing? Yep.
Approaching negative infinity.
It's going to negative infinity. And what is e to the negative x? So again, I chose the top one, the blue graph. What is it doing, Maya? It's going to positive infinity. But you're subtracting. So you've got negative infinity, and you're subtracting infinity. What do you think is happening? Jade? It's going to negative infinity. I agree. And again, you could pick a value, negative 10, whatever, put it into your calculator. To check that, Or this might be enough to convince you, no, this is what's happening, definitely. Working with infinity is different, right? Like it's not like a number. It does not always behave the same way numbers do. Sometimes we treat it kind of like a number, but it does take some practice and it does take a bit of a different kind of thinking. For example, infinity divided by infinity is not 1. It can be other things. That's an indeterminate form. So it's not just 1. But when you're adding 2 positive infinities, that's just infinity. If you're adding positive infinity and negative infinity, okay, now those are working against each other. Different things could be happening. So this does take some getting used to. But in this case, these are working together. I'm taking a really big negative number and subtracting another big number from it. That's just going to be a big negative number. It's going to be. So in this case, this would be enough evidence to show on a test. Let's go to the right. What does e to the negative x go to the right?
0.
Goes to 0. So this is similar where that part is going away. What's happening?
Oblique asymptote.
And now, is it above or below? So this is again where you have to decide which graph you're thinking of. Because if I'm thinking of this one, I'm adding it, but it's approaching 0 from below. And if I think of this one, I'm subtracting it, but I'm approaching 0 from above, so I would be a positive. So what's happening here? I'm going to consider the e to the negative x, which means my remainder is positive. But I'm subtracting it. So I'm going to be below the oblique asymptote. Oh, why? Again, you could test it. 9999, I think it's 4 nines. You could punch a value into the oblique asymptote and into the actual function, the original function, and compare them, and notice that it's below. It's very convincing. In this case, it's easier when it's not negatives. Negatives makes it harder. You just have to think a little bit more carefully. Okay, but in this case, you can tell for sure that it's below. But you could also just think about what's happening, the relationship between the remainder part and the original function, what's happening to e to the negative x. You're subtracting it, like it kind of depends. Same thing, I don't think, like on the test, I wouldn't require that you write out the word subtracting, but you have to think it. You have to think about the relationship, what's happening between them, okay? And if you punch values into your calculator to check, I think you should write them down. Like if that's the evidence that you're using to convince yourself, you might as well just write it down as an ordered pair is fine. And then I know that's what you did and that's how you came to that conclusion. Any questions about that one? I think that one's done. I'll show you the graph of that one. Not very interesting in terms of calculus because there's no points of inflection, there's no turning points, there's no horizontal, vertical tangent lines, not much happening. But this is really about exploring asymptotes and end behaviors, and so it's interesting from that perspective.
So is it below because when you compare the OA to the Y value is like less?
Yeah, exactly. Yeah.
So like if it was say like 31, then
It'd be 30.00005 or something like that, and then that would mean it's above. Yeah, so you have to find both the value of the original, of the actual function, and then the value of the oblique asymptote. And the value of the oblique asymptote might be trivial to find, because it's 3x, so it's just like 3 times. It's easy, you can do that in your head. You don't need to use your calculator for that. And then when you check the actual function, you can compare it. But what if this was 2/3 x? Then it gets really kind of messy and makes it a lot harder. That probably wouldn't come up, but you never know, right? All right, next, something kind of different. By the way, this is not ln of x cubed, which would be 3 ln x. This is ln of x all cubed. So that rule does not apply. Be a little bit careful. I will be careful on a test or worksheets, hopefully, at least they're formatted correctly, where brackets are used to determine the difference. If it was written like this, you would assume that it means that, and it would be 3 ln x. That's very different from ln of x all cubed. What do we need to know? And we talked about this in the activity and briefly talked about it in the previous lesson when we did some sketching, but we didn't really get a chance to go over it carefully. But I think that most people started to come to terms with this in the activity. When you have ln, what do you have to think? What do you have to consider? Kaylee? The domain, and what is it? It's greater than 0. So what do we do about this? A lot of people in the activity did that. This is just not a thing. We don't consider going to the left because the domain is restricted. We know that. So what do we consider? Maya? Yeah, does it have a vertical asymptote? And what do I check as x approaches? Like, this is something you just have to know. Every time you see a ln or a log, but really we don't graph logs, we're just graphing base E all the time. Every time you have to check as x approaches 0 and from the right only. Now, there are other graphs that you could come up with. And I'll talk about this after. We'll look at the work because I think there might be one question somewhere where it kind of comes up, but it's not really going to be something we have to worry about in this course. For our course, the rule is you check from the right. It's certainly possible that you could have other functions that are written differently where you may have to check from the left and the right, but for our course, we're going to stick to that. How are we going to check that? What does ln do? What does ln look like? Like that? Somebody commented last week it kind of looks like the square root function starting here. Yeah, it does. But then it keeps going, right? It doesn't stop and it doesn't go to 0. It passes through 1. If I take, so what is ln doing as it approaches 0 from the right? Negative infinity. And if you cube a big negative number, what do you get? Mohammed? A big negative number. It just makes it bigger and it's not squaring it. You're not making it positive. It's staying negative. So I think that this is probably just going to negative infinity. Once again, you could check that. I'm going to be careful here. Ln of x. cubed. Now, ln is interesting. Oh, not 10. Something close to 0? Whoops, 2112. 0.01. Are you convinced that it's going to negative infinity? That doesn't look like negative infinity. We are really close to 0, and that's not a very big number. But that is normal for ln. It does go to positive infinity to the right and negative infinity as it approaches 0, but it does it way more slowly than exponential functions. So it's normal to get these kind of smaller numbers. If you're checking on your calculator and you're wondering, that's not convincing. Like, I remember one of the questions in the activity, somebody punched in a number like this and they got like 8. That doesn't look like it's going to infinity or positive infinity or negative infinity, does it? Like 8 or negative 8? Sure doesn't. But that is normal. So you could check a few. You don't have to write them all down. I would write the biggest one, I suppose. But that certainly looks like that's what's happening. Therefore, we have a vertical asymptote. Again, you have to write this down at x, not y, x equals 0. And it's going to negative infinity. What happens if you take a big number and cube it? Just gets bigger. Looks like it has a horizontal twist at 1. Kind of interesting.
How would you know if it didn't have a vertical asymptote? Or does it?
I think we're going to see an example of that, but if you look back at if you remember back to the activity, when you plug a value into your calculator, you don't get a big number. You get something very close to 0. You get like 0.00001 or something. So you have to interpret that value that you have on your calculator. Is that a big number or a small number?
For the vertical asymptote, is that supposed to be y equals 0 instead of x?
Vertical asymptotes are x equals. This one, notice we didn't talk about the horizontal asymptote. I could have labeled it that way, I guess, but there's not really a reason to think that this one would have a horizontal asymptote, so we didn't talk about that. But vertical asymptotes are x equals. Horizontal is y equals, or oblique, I suppose. I'm going to let you try this one. We've done one like this already. So you can recognize that it's e to the something x. It's 3x, but that doesn't really make that much of a difference overall. Minus 3. So we did one like this the other day, and there was one like this in the activity. Maybe a couple like this in the activity. What do you think this one's going to have? And then you can work through it. I mean, we'll work through it together, but I'm going to let you get started on it. What if I added an x on top? How would that change it? Because that's kind of an important thing to notice, connection to make, okay, for these kinds of questions. So go ahead and see if you can get that one started. So we're going to think, you might, well, I don't know if we have to regraph e to the x. We've already done it a bunch of times. So I will give you the hint that you have to think about your vertical asymptote. So vertical asymptote, you're just setting the denominator equal to 0. This does have one. That is solvable. Now what? You have to do your testing. So that was 0.366, I think it was. So 0.36 and 0.37 or 0.38 would be close enough. Plug that into your calculator. Again, that should feel fairly familiar. The asymptote testing, I'll do that for us to speed things up. So we got from the left it's going to negative, from the right it's going to positive. Again, I'm going to speed things up a little bit here because we have already kind of done this, and hopefully you're getting the hang of this. As x goes to negative infinity, there's no negative or anything in the exponent or in front of it. I'm not subtracting. It's just e to the 3x. So this is going to negative, or sorry, going to 0 from above. So what's happening to the overall function? This is worth talking about. Yeah.
It equals -3.
-3. So y is approaching -3. Is it from above or below? And you could rationalize your way through this, I think, but you're probably better off checking on your calculator. It turns out it's from below. Also, if you're doing a full sketch, then all the other stuff that you do in terms of concavity and everything will confirm that. So you could also use that to help you. But if this is a question where you are not doing a full sketch, it's probably not worthwhile doing all the derivative stuff. So you would have to maybe plug it into your calculator and check it.
How do you know that e to the x is approaching 0 from above?
Well, because it's going to look like that. It's going to just look like that, but it's going to grow a bit faster because of the 3, but it's going to look the same. Yeah. Okay, and as I go to positive infinity, e to 3x goes to positive infinity. But what do you have to consider? Yeah.
Dx is in the denominator.
It's in the denominator. So y goes to big number in the denominator, minus 3, who cares? Going to 0. And this one is from above. And again, I would just plug 10 in, negative 10 in to check those. Even negative 10 was too big for that one. So negative 5. Just below 3, negative 3. Let's try 5. Just above 0. Right? Fairly convincing, I think. Any questions about that one? Looks like that. Again, not that interesting in terms of the calculus part. I don't think it has any, it looks like a rational function, but it is interesting that it has a different horizontal asymptote going one direction compared to the other. Yeah.
So when you're doing your testing, you use a positive or a negative based on like the x approaches, if that's positive or negative infinity.
That's right. So let me pull it back up. This one I use positive 5, so that is confirming my suspicion that this was above 0, or that is telling me, I probably wouldn't even guess, I would just plug it in. So it's telling me that it's above because that is bigger than 0. And then the previous one that I did, where I got negative 3, is telling me to the left, negative infinity, what's happening. Negative 5 is the number that I chose. That's not going to negative infinity very well, but again, exponential functions grow so fast and shrink so fast that it's very common that you have to use smaller numbers. So negative 5 is the one that I did, and it tells me that it's just below negative 3. But I found the asymptote by those other strategies. Again, I think at this point you kind of get my, what I was saying at the beginning of the lesson. You got to write down stuff. You got to, like, do you have to write down the word denominator? Or before, when I wrote down subtracting, you don't have to do that, but you have to think it. And it is a good idea to write down your thinking. Gives you something to check over later if you go back over your work. You've written something down, so you have something that you can look at. So that's something to think about. But a lot of what I'm writing is sort of for the lesson and just trying to show my thinking. But I mean, again, I would encourage you to write down as much of your thinking as you can. Okay, I'm going to draw out a few of these graphs. Whoop. What would y equals 4 ln x look like?
Just stretch
Yeah, it'd be stretched, so it'd kind of go like that. This one's a little bit trickier. What would ln of x all squared look like? I mean, if I square these positives, it would again kind of just stretch it. And then if you think back, very good, if you think back to advanced functions, we actually did a little bit of this with polynomial graphs. You take anything that's below the x-axis and you flip it above. It was absolute value, but it's the same thing if you're squaring something. So it would kind of look like this. I don't know that that's what you, if this question came up on a test, I'm not really sure that you would, that's the direction you would go. That you would graph it. You should always think, well, I'm squaring it so it's positive. So I'm taking a function, ln x, which is sometimes negative and sometimes positive, squaring it so it's always positive, and then, and kind of making it bigger, I guess. And then I'm subtracting something that is also changing in a bit of a different way. Like, I don't know that it's easy to look at that and decide what is actually happening. Ln x all squared. So what do we have to do when it's ln? We're running out of time, so I'm going to speed things up again here. Check 0 from the right. Ln of x all squared is going to positive infinity. 4 ln x is going to negative infinity, but you're subtracting. So you're taking a big number and subtracting a negative number. So you're adding another big number. So don't you think this is probably going to positive infinity? And sure enough, if I check on my calculator, although interestingly, x equals kind of like we saw before. I don't get a very big number, but I sure don't get something that goes close to 0. What can happen, and again, we've talked about this, but you need to know this, as you're approaching 0 from the right, you could go to positive infinity, like this one does. You could go to negative infinity, or you can go directly to 0. So you have to put this into your calculator and interpret it.
Do we have to show like something in a value on the test?
I think that the test says you have to show some evidence. So if you could also just write it like this, right?
Yeah.
That's an easier way. Like I said, if you put something into your calculator, why not write it down? Just so, like, it takes nothing to write down an ordered pair. So I would say do that. But it's not really about what's required. You have to show some evidence. So, and as long as you get the right answer, you're probably going to be safe. Huh. This one's a tricky one. How come? John? Yeah. We've got an infinity and another infinity, but we're subtracting. So it's almost like which one is growing faster. Okay? And I mean, if you did enough work with this stuff, you might be able to kind of figure out the likelihood of which one grows faster, but that's not something that I would anticipate. So again, I would just sub in a number. And in fact, watch this. I'm going to sub in 10,000. And I got 86.5. What's relevant about that?
It's kind of small.
Yeah, it's pretty small. You would think that if it's going to positive infinity, it would be bigger, but that's just the way ln works. It's just the way logarithms work, so sure enough, that is going to positive infinity. But really slowly. That's an interesting graph. It's got a little bit of stuff going on. It's got some points of inflection, some changes in concavity. It's got a turning point minimum, kind of an interesting graph. There is one more in the lesson. We're obviously not going to get to it. You can try it yourself. What's that one going to have?
Okay, just a question about the-
Yeah, about the last one, sure. Go ahead.
So like if the value was like 0.00005 or something, it would be negative infinity?
No, 0.0005 looks to me like it would be going to 0, which there's not really a reason to think that function would. To the left, if you got 0.0005, that means it's not going to positive infinity, it's going to 0. If it was going to negative infinity, it would be negative 80 or negative 90. Or if it was some other number like 5.00001, then I'd be like, well, it looks like it's going to 5. But there's no reason to think that this graph would do that, so that would not probably happen. But if you did put in a big number and it was close to some other number, 5.000, 6.00, that looks like a horizontal asymptote. What do you think is happening in this one? There was one like this in the activity that was really important. We do have a couple minutes left. This one, when I go to the left and e to the x goes to 0, what's left over? Okay, let's write it out quickly. What's 8x divided by negative 2? That shouldn't be hard. You've been doing that for years. Feels a little bit different because this is all kind of new. So what is it?
Wouldn't we start with the vertical asymptotes?
Yeah, you would. I'm skipping that part, I guess, because I wanted to talk about this part, but yes. I mean, and also, it doesn't matter what order you do it, but you're right. I often do it in the right order. We're just about to run out of time. So what is that? Isn't that an oblique asymptote? Okay, and I'll leave the rest for you, and you can compare your answers with the scanned version online. But now you have to check if it's above or below, which is a little bit tricky with these kinds. And then also, yeah, go back and do vertical asymptotes and check what is happening to the right.